So, we continue our discussion of mean values of multiplicative functions which take values in the unit disk. As we saw last time, the motivation was to study real valued functions such that, and we are interested in a limit law and our question is, does a limit law for such a function exist? By limit law we mean the proportion of numbers, or rather the density of numbers for which f of n is less than or equal to x. Okay, so the question is, does this converge to some function? Let's call it capital F is usually used for the cumulative distribution function. So let us call it, say. Okay, so this is the fundamental question we want to answer, and last time we learned by probability theory that to answer this question we need to show, it is to say that such a function has a limit law is equivalent to showing the existence of the limit (1 over n summation n less than or equal to n), okay, e raised to the I t f of n. Okay, if this exists, if this limit exists for every t, and if you can show that this is equal to some function, let us call it phi of t, which is continuous at 0, then this is equivalent to saying that your original function has a limit law. Okay, so this was the motivation, and now you see over here, this is basically the mean value of an arithmetic function which seems to be taking values exactly on the unit circle if this is a real valued function. More generally, as we initiated the discussion our discussion last time, what we want to do is we want to study some special functions which could possibly take values either on the unit circle or inside the unit circle. That is a more general scenario. So, we stated this theorem of Delange and started proving it, and this is the discussion that we continue today, and this particular theorem has lots of ramifications and applications, which is what we are going to study over the next few lectures. So, here is the situation. So, let g of n be a multiplicative function such that, and g is a complex valued function such that, actually, so we want not just any complex valued function, we say that where D is the set of all the complex numbers whose absolute value is less than or equal to 1. Okay. So, let us have such a multiplicative function with the condition that suppose you sum over all the primes p and you consider the series 1 minus the real part of g of p over p if this is finite, then this mean value of this function g turns out to be equal to a quantity that we call m of g, and I will just define it in a second, plus little o of 1 as actually, since we are writing x going to, we are taking the limit. So, this limit is equal to m of g, where m of g is defined as the following product. This is a product of all the primes up to x, and you have inside, so you have 1 minus 1 over p times, for each prime p, this is the factor that you have to take. So, nu going from 0 to infinity, g of p raised to the nu, okay, over p raised to the nu. This turns out to be the mean value of this function g, provided these conditions are satisfied. Now, we start proving this theorem. Let us briefly recall some important facts about this. So, why do we have this type of a function? So, what we do is, we take this function g and we take local, we study local versions of g. So, what we do is, given such a function, like sort of a universal function g, let us take y to be greater than or equal to 2. Any number y, let us fix it for the meantime. So, what we do is, we consider the function which is multiplicative, and let us call this g sub y, such that, so to define a multiplicative function, you need only specify what happens at prime powers. So, for any prime power p raised to the nu, okay, if the prime is bounded above by y, then this takes the value as in g, and if p is greater than y, then it takes the value 1. Okay. So, if you define a multiplicative function g sub y in this way, this is very close to g, and it becomes closer and closer to g. We need to specify what closer and closer means as y goes to infinity. As y goes to infinity, for more and more numbers n, g sub y would match g exactly. All right. So, now the thing is, let us first derive the mean value of this function. Okay, remember, we are taking y to be a fixed number. So, this is something that we started doing last time, and here we use a simple principle. So, if you have g sub y, suppose you can write this to be equal to some function, suppose you can find some function h such that g sub y of n is equal to the sum of all those h y at d's, where d runs over divisors, positive divisors of n, then this is a technique that we have repeatedly used in our class. If you want to sum up g sub y of n, okay, you put this in the inner sum and you do an interchange of summations, what you end up getting is equal to sum over h sub y of d times the greatest integer x by d as you run over all the d up to x. All right. So, we are trying to, since this is the quantity we are interested in, we need to find out a corresponding h sub y which will satisfy this condition. But recall by Mobius inversion that if there is such an h sub y, it can be found out by inverting, taking the Mobius inversion of this equation here. So, it turns out that h sub y is equal to the Mobius inversion of mu and g sub y. Now, g sub y is a multiplicative function, the Mobius function is a multiplicative function, therefore, your h sub y is a multiplicative function, and you need only specify what h sub I is at prime powers, right. And we saw this last time, which was not at all difficult to see. We saw that h sub y of p raised to the nu is equal to, okay, we need to, for nu equal to 0, this is just 1. So, h sub y of 1 is just 1. Okay, so, what we have is g sub y of p raised to the nu minus g sub y of p raised to the nu minus 1 if your nu is something greater than or equal to 1 and your prime is less than or equal to y. Okay. In fact, for even for primes greater than y, you can write out the same expression. So, what we are saying is, if p is up to y, we have g of p raised to the nu minus g of p raised to the nu minus 1, and it is 0 if nu greater than or equal to 1 and p is strictly greater than y. I leave it as an exercise for you to verify that this is your h sub I. All you have to do is just use this Mobius inversion, mu star g sub y. This is exactly what you will get. You have to evaluate it at prime powers. We know what the prime powers of p to the nu are. They are of the form p to the k as k runs up to nu, and this is how we go about doing this. So, what we have is, because of this fact, what we end up getting is that this sum of g sub y of n, as n runs up to all the n runs over all the natural numbers up to x, what do you get here? This is exactly equal to, again you run over all the natural numbers up to x, h sub y of d times the greatest integer of x over d, right. And we know what we are doing next. We need to isolate the main term and the tail, or rather the error term that goes to 0. So, we write this as h sub y of d times x over d plus O of summation d up to x h sub y of d, and then we isolate again. What we do is we first take the entire sum, okay, so x can be brought out, h sub y of d over d minus x times summation d greater than x, okay, of h sub y of d over d, okay, plus you have an error term last time we saw that this particular sum, okay, because using the fact that h sub y is multiplicative, you can write it out in terms of an Euler product, provided of course either you know that the sum converges absolutely or the corresponding Euler product converges absolutely. That can be shown That is not difficult, using the fact that absolute of h sub y of d is at most 2. Okay. So, if d is any prime power, that is. So, this turns out to be equal to something we had discussed last time, x times product over all the primes up to y times 1 minus 1 by p times the sum g of p raised to the nu over p raised to the nu going from 0 to infinity. Okay, so this part is taken care of. Now, what we have is this remaining thing, which we show to be something which is little o of x. We want to find an upper bound for this and this. So, let us do one thing. Let us define h sub y of x to be equal to our x times summation d greater than x absolute h sub y of d over d, okay, plus you have this other thing here, d up to x absolute of h sub y of d. Okay, now if d is greater than x, that means x is less than d. Okay, so x over d is strictly less than root x by d. This is true when x is less than d. So, this is less than or equal to root x times d greater than x absolute h sub y d over root d. Okay. And if x is greater than or equal to d, then x over d is clearly greater than or equal to 1, and therefore square root of x over d is also greater than or equal to 1. So, this inequality would hold okay. Why does it help us to separate out root x instead of the full power of x? We will see that soon. So, what we have is, this is just root x times summation d going from 1 to infinity absolute of h sub y of d over square root of d. Now, this is a multiplicative function. Whenever h sub y, whenever your function is multiplicative, so is its corresponding absolute value. So, therefore, if we can show that the corresponding Euler product converges absolutely, then so does the sum, and so this can be treated just like some constant. So, what do we have here? It will be the product of all the primes up to y, and what will we have? So, you have summation nu going from 0 to infinity absolute of, these are, each of these Euler factors is just this, p raised to the nu over p raised to the nu. Now, absolute of h sub y of p raised to the nu is something which has an absolute bound, the absolute bound being 2 because of the way you are defining. Each of this has absolute value bounded above by 1, therefore, absolute of h sub y of p raised to the nu has to be less than or equal to 2, and okay, this is a square root, so we have to be a little careful, nu over 2, okay. Then using that bound, what we end up getting is that this is less than or equal to product over all the primes up to nu. Okay. So, take nu equal to 0 out, plus then you go from nu going from 1 to infinity. So, you have summation 1 over p raised to the nu over 2, since that corresponding constant has been taken out. Okay. So, each of these will or rather let's be a little careful here. Let's write this as less than or equal to, and let's say 2 times summation nu going from 1 to infinity 1 over p raised to the nu by 2. So, this is just a geometric sum, right? And so, what you end up getting is, this is just maybe I will write it here, product of all the primes up to y what do you have? You will just end up having 1 plus 1 over root p times 2 over 1 minus 1 over root p. Okay. This is, so this is something very absolute, right? This is an absolute bound for each Euler factor, and there are only finitely many Euler factors. Therefore, this is something which is absolutely convergent, and therefore, the corresponding sum here is also absolutely convergent. And in fact, it just turns out to be, what is this? This is just, this turns out to be some constant that will depend just on y. Okay. So, this is equal to some constant. So, so this is less than some absolute constant c raised to the omega of y, because for any prime p, this whole thing is bounded above by some absolute number. Let's call it c, and then there are omega of y number prime factors up to, okay, not omega of y, but the number of primes up to y, right? So, this is something that depends only on y is a fixed number. So, what we have is root x times some constant that depends on y. So, what you have is that, so we get that our summation n less than or equal to x g sub y of n turns out to be equal to x times m of g sub y, referring to this infinite product over here, okay, plus, okay, root x times a constant that depends only on y. So, this is just little o of x, since you just have root x here. So, what is this telling you? As x goes to infinity, the mean value or the average order of g sub y of n is just m of g sub y. Okay. How do we go from g sub y to all of g? That is the rest of the proof. So, to do this, what we observe is the following. Now, what we actually try and do is, we just consider these m's, okay, m of g sub y, and we try to understand what happens as y goes to infinity. Since to go from g sub y to g, you have to let y go to infinity. So, we do the same with the corresponding m of g sub y. That is our first question. Delange's innovation and the entire technique around this theorem and other theorems related to this technique is to convert this problem, twist it a little by certain exponentials. Okay. So, what they do is, in fact, from the above, one can observe by almost exactly the same technique that if you were to take the function g sub y of n times e raised to the minus I of some function, let's call it b of y, or let's call it a of y, where a of y is real valued, okay, then exactly a similar kind of a technique will give us that this is equal to x times m of g sub y times e raised to the minus I a of y plus little o of 1 as x goes to infinity. Okay. So, sometimes we may also choose to put a subscript below this O to specify what the asymptotic, what variable the asymptotic is describing. So, this is an estimate that we write and we record. This will come in handy. Okay. Now, what we do is we want to show, we will show that for a specific type of a function A, this function m of g sub y times e to the minus I a of y is a Cauchy sequence. Because it is a Cauchy sequence, it converges. Okay. And using the limit of that Cauchy sequence, we derive the mean value of the original function g that we have started off with. So, we show the following. So, here is how we define a function A. So, let us do the following. You see, your g of n, you told me, is a function that could take complex values, but with absolute value at most 1. So, g of n can be written as absolute g of n times e raised to the I times what you call the argument g of n, where argument is some angle, let us say lying between 0 and 2 pi. Now, what we do is we consider g of p raised to the nu, okay, and we define, so define an additive function theta of n. Okay, again, to define an additive function, it is sufficient for us to describe what that function is at prime powers. So, such that theta of p raised to the nu for any power of a prime is equal to the argument of the corresponding value of g at p raised to the nu, if provided g of p raised to the nu is not equal to 0. If it is equal to 0, then we just take theta to be equal to 0. Okay, so what are we doing? We are writing g of n in terms of its absolute value and its corresponding angle. Then we are taking the angle for p raised to the nu and generating an additive function from that. Now, that additive function is real valued. It may not necessarily lie between 0 and 2 pi. We are not taking it modulo 2 pi. We are not taking it in a periodic way. We are just taking it to be the sum of the corresponding argument of g of p raised to the nu. This is how you generate this additive function. Okay. With this in place, what we do is we define for any number y, which is say greater than or equal to 2, define a of y to be equal to sum of theta of p, okay, over p, where Now, this is an additive function. If we were to try and evaluate its mean value, we would have to in fact use, we have a very good technique available with us, namely the Turan-Kubilius inequality. So, let us see how that will help us. First, like I mentioned, we are going to try and show that with a of y as defined here. So, our claim is that m of g sub y times e raised to the minus I a of y is a Cauchy sequence. But to do that, we want to somehow use this fact here. Okay. So, what we do is, so by star, let us call this equation star. Recall by star that if we want to show that this is a Cauchy sequence, it will be sufficient to show, okay. So recall, so first of all, what does star actually mean? Okay, for any epsilon, there is a large enough x, we have summation n less than or equal to x, g sub y of n e raised to the minus a of y, write this as 1 over x minus m of g sub y e raised to the minus I a of y. This absolute value is less than epsilon for sufficiently large x. So, instead of focusing on this bit, suppose we just focus on this bit. Okay, let's consider this term, and let us show that this is a Cauchy sequence, okay, where you take y and z separately. So, this if you can show the corresponding Cauchiness of this part, it would immediately imply that this too is a Cauchy sequence, because the difference between them can be made very, very small for very large values of x, which is what we want. So, it will be sufficient therefore to show that this bit here, okay, for our x being very, very large, this term, first term here is, it forms a Cauchy sequence as you vary y. Okay. So, what we do is we define the following function. We first take, okay, let us just define s x y z, okay, to be equal to 1 over x times summation n less than or equal to x g sub z of n e raised to the minus I a of z minus 1 by x. Okay, let us take this to be summation g sub y of n e raised to the minus I a of y. Okay, where let us take z to be something greater than or equal to y. So, what happens now? Absolute, define s x y of z, and let us see what happens as y and z become very, very large with z greater than or equal to y. So, absolute of s x y z is less than or equal to 1 by x times summation n less than or equal to x absolute of g sub z of n e raised to the minus I a of z, okay, minus g sub y of n e raised to the minus I a of y. Now, this g sub z of n, what is it equal to? This is just product of p less than or equal to z, okay, of our, since this is a multiplicative function, g sub z of p raised to the nu, let us henceforth denote, wherever required, nu to be the highest power of p dividing our number n, okay, and you have e raised to the minus a of z, where a of z is also clubbing together all those primes which are up to z, okay. Now, here in this other term, we have all the products or the product of all the primes up to y. So, but there are some more terms here. So, what we do is we take this term and split it into two parts. One is the product of all the primes up to y, and then there are all the primes which are greater than y and less than or equal to z. Once we do that, then we can take that part common from both the terms, okay. Now, there is some commonality between a of z and a of y as well, okay. By exploiting properties of complex numbers, what we end up actually deducing is the following. This is described in the notes in detail, which I will share with you, but it is not very difficult to verify this. What we end up getting is the following. Your absolute of s of x, y of z turns out to be less than or equal to the following. Here is what we have: 1 by x summation of n less than or equal to x, okay, times absolute of, so first we run over all those primes lying between y and z, so strictly greater than y and less than or equal to z. We take these primes and we take absolute value of g raised to the p raised to the nu times, actually here we do not need to take absolute value, we can just take g of p raised to the nu times e raised to the minus I a of z okay. So, what you have is some complex number, this being the absolute value of that complex number times the, actually this is not, so g, you have some number product, okay, let me break this down carefully. You have a product of g of p raised to the nu, where, so nu refers to the highest power of p dividing n, but you are only taking those primes p which lie between y and z, and you have e raised to the minus I a of z minus a of y. So, this is basically the sum of all those primes again lying between y and z, theta of p over p. Okay. So, you have some complex number minus 1. When you simplify this further, here is what you get. So, what you have is, so let me write this as 1 by x summation n up to x. Keep the product intact. So, you have product over all the primes lying between y and z. Okay, take the, there is an absolute value. Okay, p raised to the nu is the highest, nu is the highest power of p dividing n. Now, this g of p raised to the nu, you can write it as absolute of g of p raised to the nu times e raised to the I of the function coming from the argument, right, which we call theta of p raised to the nu, right. And we have here with this, so this takes care of this term. Then we also have e raised to the minus I of summation y less than p less than or equal to z theta of p over p. Okay. So, first you have this product inside. This is just the simplification of this part g of p raised to the nu. Okay. We specify what are the angles and what is the absolute values. Then you have e raised to the minus I of a certain sum which is coming from primes lying between y and z, and you also have finally minus 1, that is a different term altogether, it is not part of any of this product or sum. You have this here. So, what happens now is this sum and this product, they can be combined together, right, and simplified as following. So, here let me just mention a small inequality which is as follows. Suppose you have some number b and you have e raised to the minus I theta minus 1, okay, where b is some real number. Okay. This can be shown to be less than or equal to absolute of b minus 1 plus absolute of e raised to the I theta minus 1. I leave this verification as an exercise for you. So, with this, okay, using this to the weird looking term that we have here, we end up getting that absolute s of x, y, z is less than or equal to, we end up getting 1 over x summation n up to x, okay, times product of all the primes running between y and z and just the absolute of g of p raised to the nu, where this is just the highest power dividing n. Okay. We write this minus 1, we write this. So, this part is b, this product, and the other one comes from the corresponding angles. Okay. But when you take a product of exponentials, that is simply exponential of the corresponding sums. When you take it into exponential, the products change into sums. So, what do you have here? Plus 1 by x into summation n up to x, okay, times absolute value of e raised to the minus I of a of z minus a of y, okay, coming from here, but we also have to take into account the theta of p raised to the nu, the corresponding one. So, we do that by defining another function, additive function theta sub yz of n, okay, minus 1 absolute value, where theta y sub z of n is an additive function coming from all those prime powers with primes lying between y and z. So, just like we considered the additive function theta of n, this is just a reduced form of theta of n as follows, okay. So, here this is an additive function given by what is our function here? It is given by theta sub yz of p raised to the nu is equal to theta of p raised to the nu if the prime p lies between y and z, and if not, then you just take 0. Okay. So, you had an additive function theta of n, you reduce that additive function to another additive function with the restriction for primes lying between y and z. Okay. So, to summarize so far, what we have is the following. You have got your S of x, y, z to be less than or equal to the sum of two absolute values of two complex numbers, okay. Let us look at them separately. This part is where we will actually use our Turan-Kubilius inequality, but let us first address the first part here, okay. So, let us denote R of p raised to the nu to be equal to absolute of g of p raised to the nu, okay, instead of writing absolute values all the time. What do we know for this number? We know that each of these numbers is bounded above by 1, therefore, the product is also bounded above by 1, right. So, what do you have? So, 1 over x times summation n less than or equal to x. So, you have summation y less than p less than or equal to z. Okay. So, before I write this, actually let me mention another little inequality. If you have any bunch of complex numbers and real numbers in particular, with absolute value of each of them less than or equal to 1, then the product of these numbers u1, u2 up till u sub k minus 1 turns out to be less than or equal to summation j going from 1 to k corresponding uj minus 1. We apply this inequality, I leave this inequality as an exercise for you to verify. We apply this inequality to the first term here, product of certain numbers, each of which is less than or equal to 1. Okay. So, what we have is thus 1 over x summation n up to x, okay, absolute of product y less than p less than or equal to z r of p raised to the new minus 1 is less than or equal to 1 over x, nothing happens to the outer part. It is in the inner part that we are going to convert this product, bounded above by a corresponding sum. What is this sum? The sum runs over all the primes lying between y and z, okay, absolute of r of p raised to the new minus 1. Now, what do we know about r of p raised to the new? It is a positive number, non-negative number bounded above by 1. So, this absolute value can just be written as 1 minus r of p raised to the new. Okay. Whenever we see two sums, we interchange it, and now you see what is happening. And remember, we are running over what is new here? Nu is the highest power of prime p dividing n. This is important. This is how the inner sum is related to the outer sum. So, what do we have here? So, the sum we write as, so 1 over x, we do not do anything to that. Okay. Now, the outer sum runs over all the n up to x, and the inner sum runs over all the prime powers dividing n. So, if you were to interchange summations, what would you do? First, you would take all those prime powers, all those primes and all those corresponding powers which are bounded above by x, and then in the inner sum, you take all those multiples, all those numbers for which the corresponding prime power is the highest prime power dividing that number. So, to explain this more, what we have is, first you are running over all those primes which lie between y and z, and then, so actually you are running over all the primes. So, this is actually a double sum. You are running over all the primes and all the corresponding powers nu such that firstly p lies between y and z, okay, then p raised to the nu is less than or equal to x. Whatever prime you may take between y and z, just make sure that you take only those powers for which p raised to the nu is bounded above by x. Then bring 1 minus r of p raised to the nu outside, and then what are you left with inside? Inside you are left with all those n's up to x for which p raised to the nu, so the outer sum is over all the p raised to the nu, and the inner sum is over all the multiples of p raised to the nu for which p raised to the nu is the highest power dividing n. Okay. So, in other words, this just is x of p raised to the nu minus x of p raised to the nu plus 1. Either ways, this is certainly less than or equal to, this term is certainly less than or equal to x over p raised to the nu. Okay. So, you have 1 over x times x, bring that out and they cancel each other, p nu such that p lies between y and z, and p raised to the nu is less than or equal to x times 1 minus r of p raised to the nu over p raised to the nu, right? Okay. So, how do we simplify this further? This is, remember, I am going from an equality to an upper bound. which will serve our purposes. Now what we do is, we take those powers nu which are exactly equal to 1 and those which are strictly greater than 1. So we write this as, so if nu is equal to 1, then all we have is the bounds for p. So we run over all those primes p for which, okay, p raised to the 1 is less than or equal to x. I mean, it is more important for us that p must lie between y and z. Okay. Let us, in general, we will take x to be very, very big. It would be larger than y and z. All right. So this is not imposing a restriction to us. So 1 minus r of p over p. Next one. Here you run over again all those primes which lie between y and z, but now you are taking prime powers nu which are at least 2. Okay. So nu is greater than or equal to 2 and p raised to the nu is less than or equal to x, okay, times 1 minus r of p raised to the nu over p raised to the nu. All right. But now the advantage of dividing this into two different sums is, the second sum now starts from p square. Okay. So this is less than or equal to, the first term we leave intact as it is, y less than p less than or equal to z, 1 minus r of p over p. The next term we exploit the fact that nu is at least 2. So what do we have? Plus sum over all the primes which are strictly greater than y and bounded above by something as well, but p greater than y is important for us. And then you have learnt to say that p raised to the nu is less than or equal to x is to say that nu is less than or equal to log x by log p, right. So what we have is, but you have an inequality here less than or equal to, so you can actually say that this finite sum with non-negative terms is less than or equal to an infinite sum with the same terms, okay, non-negative terms. So what you have is nu greater than or equal to 2. Now 1 minus r of p raised to the nu is definitely bounded above by 1. Okay, so you have 1 over p raised to the nu. Now this sum is starting from, this is a geometric sum starting from 1 over p square. Then you have 1 over p cube and so on. You sum this up, what you end up getting is 1 over p times p minus 1, which is something of the form bounded above by some constant over p square. Okay. And now your p is greater than y. So you have sum of 1 over p square where p is greater than y, okay, that can be bounded above by O of 1 over y. So this turns out to be, this is equal to, actually again less than or equal to (1 minus r of p over p), okay, plus O of 1 over y. Some, it is bounded above by some constant multiple of 1 over y, right. So in our evaluation of s, x, y, z, okay, the part that is coming from the absolute value of your multiplicative function is mentioned here. Now we have the other part remaining. We have to look at what is the other term coming from 1 over x summation n less than or equal to x, okay, absolute of e raised to the minus I a of z minus a of y minus this function theta yz of n, okay, minus 1. Now, here we use another inequality which is helpful to us. We use e, suppose you have any real number theta, then absolute of e raised to the I theta minus 1. This can be written, actually we can write this as integral 0 to t, 0 to theta of e raised to the it dt, right, okay, and by applying the standard inequalities, it can be shown that this is absolute of e to the it is always 1. So, this thing is less than or equal to 1 times the length of the interval, which is theta. There is an absolute value outside. So, whatever your, if as long as theta is a real number, positive or negative, absolute of e to the I theta minus 1 is less than or equal to absolute of theta. Okay. So, we exploit that again here. So, we have that this term here is less than or equal to 1 over x summation n up to x, and then what you have is absolute of a of z minus a of y minus theta yz of n. Okay. Now, we apply the Cauchy-Schwarz inequality here, okay, right. This absolute value can be treated as 1 times this absolute value. So, applying the Cauchy-Schwarz inequality accordingly, what we have is, so 1 over x into summation n less than or equal to x 1 square, which is just 1, raised to the half times summation n less than or equal to x of a of z minus a of y minus theta yz of n whole square. So, theta yz of n minus whole square, okay, and then the whole thing raised to the half. But what is this? This is O of x to the half, right. So, this is less than or equal to summation less than or equal to 1 by x times this summation n up to x of theta yz of n minus a of z minus a of y whole square, the whole thing raised to the half. Why is it important for us? Why is it helpful for us to reduce this into evaluations of sums of corresponding squares? Remember, your theta yz of n is an additive function. So, you have an additive function f of n minus a certain sum whole square. You have learned to evaluate or estimate that particular sum with the help of Turan-Kubilius inequality. Okay. Now, how do you apply the Turan-Kubilius inequality here? See, this sum theta yz of n, this is an additive function, right. So, this is summing over all the prime powers where primes lie between y and z, whereas this a of z minus a of y is just your theta of p over p, where your when you were applying Turan-Kubilius inequality, what you had was all possible for the corresponding functions, you had theta of p raised to the k over p raised to the k. You summed over all the corresponding prime powers. But over here, you are only taking k equal to 1. So, you have to apply the Turan-Kubilius inequality and then also account for what contributes most, what is the contribution from k equal to 1 and what is the contribution from k greater than 1, which would be minimal in order. So, let me just write this down here and we will take this up in our next class. Since we have spent so much effort into learning the Turan-Kubilius inequality, we might as well also learn how to apply them wisely. So, what is the Turan-Kubilius inequality? How does it apply here? So, I will let you think about this over the weekend, over this week, and then we will also prove it. So, what you have is 1 over x summation n up to x theta sub y of z. So, whatever inequality you have learned for additive function, apply it to this particular function, theta of y z n minus a of z minus a of y whole square. This turns out to be less than or equal to 1 over y, and so you have the square and of course you have the whole thing raised to the half, which is what you need. You can show that this turns out to be less than, actually not just less than or equal to, less than 1 over y plus summation So, let me write out 1 over y plus, let us write down y less than p less than or equal to z theta of p whole square over p, plus half plus 1 over square root of y. And so, your 1 over y can get absorbed. By applying Turan-Kubilius inequality and studying the tails in each of the estimates for the sums coming from the expected value as well as the deviation carefully, this is the inequality that we will end up deriving. So, I will conclude today's class with this as an exercise. In our next class, we will prove this, we will understand how Turan-Kubilius is used, and then we will put all of this together to show the Cauchiness of the sequence that we wanted, and that will immediately tell us the mean value of the multiplicative function that we are after. So, we will learn how all the conditions in Delange's theorem are important to prove that estimate. So, I stop for today.